Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus and consider two numerical methods that are often used to solve equations, find zeros, find local mins and local maxes, and several other things along the way. And those two methods are called the bisection and the Newton methods. The bisection method does not require calculus, but the Newton's method does. So, it gives you some tools in case you forget how to know calculus on how to solve these kinds of problems, and if you happen to know calculus, you will have a slight advantage over the bisection method, and we're actually going to show the pros and cons for both of these in this discussion. So as a common example, let's assume that we have the function f of x, which is equal to x squared minus 2, defined on the domain r greater than or equal to 0. So we should know what this curve looks like. So since we're defining on the non-negative real line, then this curve is going to be the right-hand side of this parabola, right? So let's assume that this is our x and our y-axis as usual. So obviously that this point is going to be our minus 2, that's our vertical shift. And there's one point of interest, and that's going to be this point here. So what is this point equal to? Some people will define it as this symbol, square root of 2, and we can use a calculator to say calculate that, but how exactly do we find this number whose name we give square root of 2? Because not all roots have pretty names. This is just a common example of where elementary function definitions and practicality sort of butt heads against each other. So, how can we find the true value of this point whose name we give the square root of 2? Again, we do not necessarily have to have such a beautiful function and a name for this beautiful number, but this is just to sort of guide your intuition behind what is going on between these two methods. So there's one theorem that I need to introduce that we're going to take advantage of for the first method, and it's the following. This theorem often goes by the name of the intermediate value theorem and sometimes abbreviated by just IVT, and it states the following. Suppose that f is a function that is continuous on some closed interval ab with f of a, f of b both defined and them having a product that is less than 0. Which means that if one is positive, the other must be negative, or if one is negative, the other must be positive. Nonetheless, they both have to have different signs. If you have that f is continuous on that interval AB, and the product of its evaluation endpoints are opposite signs, then the intermediate value theorem guarantees there exists another number c in between a and b, such that when you evaluate the function at that point c, you will get equal to 0. We might not know what c is, but c must be there. So what exactly does that mean in terms of our example? So if we evaluate this curve at, say, some point A, and we get a negative number, and we evaluate this curve at another point, say B, and we get a positive number, notice that they give you opposite signs. That means there must exist some point in between A and B such that this continuous function crosses the x-axis. There could be many, but there's at least one in between A and B. So let's see if we can find an A and B that make this true for our example. So our example is f of x is equal to x squared minus 2 for x greater than or equal to 0. So let's start off by plugging in some nice numbers. Let's start with 1. So f of 1 is going to be equal to 1 squared minus 2, which is 1 minus 2, which is going to be minus 1. If we plug in 2, we're going to have 2 squared minus 2, which is 4 minus 2, which is positive 2. Notice that these points, these values, have opposite signs. And we know that our function is a polynomial, and this is continuous on its entire domain, right? Also, it's differentiable on its entire domain as well, but more so, the intermediate value theorem just requires it to be continuous. So since it has opposite signs, what does that mean? That means that there exists, so backwards e means there exists in shorthand, there exists a number c in between 1 and 2 such that f of c is equal to 0, right? So whatever the square root of 2 is equal to, it's between 1 and 2, right? So it's 1 point something. So that means we already have the integer portion of our solution, right? Now we just need a couple more decimal accuracies to make it a little bit more precise. So let's formally state the steps that the bisection method is going to have. So the bisection method, some people call it the bisection iteration method. So the first is to find our intermediate value theorem interval A and B. The second thing that we need to do is to evaluate f of A plus B over 2. And we have a couple things that could happen. 3. If f of A plus B over 2 is equal to 0, then A plus B over 2 is our solution. And if f of A plus B over 2 is negative, we're going to replace it. So we're going to replace A plus B over 2 with the minimum of A and B. 5, if f of A plus B over 2 is a positive number, we're going to replace A plus B over 2 with the maximum of A and B. Because keep in mind, for A and B, we're going to have a lesser and a greater one, right? Now, keep in mind, we are only associating these for a increasing function. So this is for increasing. If it happens to be a decreasing function, you're going to swap these particular numbers, right? So obviously, if we get 0, then we're going to be pretty much ending our iteration. And obviously, if we do not get 0, then we need to make our interval a little bit more finer and finer. So to illustrate this algorithm, let's actually walk through a couple of steps just to make sure you get it. So we know that f of 1 is equal to minus 1, and f of 2 is equal to 2. So since these are opposite signs, that means there's a point in between 1 and 2 such that f of c is equal to 0. So what we're going to do is we're going to divide the interval 1 and 2. We're going to cut it in half, i.e. we're going to bisect it, which is going to be 1.5, which you can find just by doing 1 plus 2 divided by 2. And when you plug in 1.5 into your original function, you're going to get 0.25, right? So what does that mean? So f of 1.5 gives us a positive number, so we're going to be replacing 2 with 1.5. Right? Because what does that mean? That means, well, obviously our function was positive at x is equal to 2, and it's also positive at 1.5. And since it's positive at x is equal to 1.5, and it's negative at x is equal to 1, that means there exists a number between 1 and 1.5 such that f of c is equal to 0. So we're fine-tuning our intermediate value theorem interval smaller and smaller, half by half on each iteration, right? So this is our first iteration, or our first iterate. And our second iterate is going to be the following. So obviously f of 1 is still our negative, but f of 1.5 is going to be our new positive. So f of 1 we know is going to be negative 1, and f of 1.5 is going to be equal to 0.25, which means there's a number in between 1 and 1.5, and in particular that's going to be equal to 1.25, such that there exists a point between 1 and 1.5 that gives us a 0 there. So one can find that f of 1.25 is approximately equal to negative 0.4375, which is a negative number, which means we're going to be replacing 1 with 1.25, right? Because 1.25 is somewhere here, which means there exists a number between 1.25 and 1.5 such that f of c is equal to 0, right? And we're just going to keep repeating and repeating until you get the precision that you want. So now we're going to have f of 1.25, which is approximately negative 0.4375, and then f of 1.5, which we knew to be equal to 0.25. So it switches signs, negative to positive or positive to negative. Each one of them is perfectly okay. And then we're going to be taking the average. So f of 1.25 plus 1.5 divided by 2 is going to be f of 1.375, which we can evaluate to be approximately negative 0.109375, which is a negative number, which means we're going to be replacing 1.25 with 1.375, and that's going to give us our next iteration. So iterate number 4, we're going to be looking at f of 1.375 and f of 1.5, and then the average of the two. 109,375, and that's going to be equal to 0.25. So that means the square root of 2 is somewhere between 1.375 and 1.5, right? So let's see where this next iteration is going to take us. So 1.375 and 1.5 average out to f of 1.4375, which is going to come out to approximately 0.0664065. Notice that our evaluations are getting closer and closer to 0 from both sides. That's our limiting procedure. Right? So our next iteration would look like what? So iterate number 5. So this is positive, which means we're going to be replacing our positive upper bound. So we're going to have f of 1.375 and f of 1.4375, which is approximately equal to negative 0.109375. That's approximately 0.0664065. Right? And we can continue on and on and on. But if we stop at iterate number 5, then we can say what? That means the square root of 2 is strictly between f 1.375 and 1.4375. And that gives you an approximation for the square root of 2. And that's after 5 iterations. And you may think, well, I don't even know what the first decimal digit is, and you might be right with that, but nonetheless, the range is still relatively small, within a tenth, right? Because keep in mind the square root of 2 is approximately equal to 1.4142, which definitely satisfies that. But, if we continue more iterations, then we should get a more accurate solution. But definitely 5 iterations doesn't even give us that first decimal place. Obviously, this has what we call slow convergence. So question, can we do better than this? And the Newton's method does such that. So although the bisection method definitely will converge eventually, the convergence rate is really small. So now we introduce the Newton's method, which is definitely a lot more better than the bisection method in terms of convergence speed, but it requires you to know a little bit of calculus. So the Newton's method starts off with step 1, which says we need to choose an initial guess. Sort of like the bisection method requires us to choose an initial interval for which the intermediate value theorem makes sense. So let's assume that for our particular example, which was y is equal to x squared minus 2, we choose our initial guess to be equal to, say, 1. And obviously this is for estimating the square root of 2. Because we already know that when we plug in 1, then we get some number that is slightly negative, and 2 gives us something slightly positive. So it's around 1 point something. So what Newton's method does is it goes down to f of 1, and it considers the line tangent to the curve at this point. Right, so that's the line tangent to the curve. And the point for which this tangent line intersects the x-axis, that's going to be our next point. Once we get our x1, then we're going to plug it into our curve and find the tangent line at x1 fx1, and that's going to give us this particular point, and the point for which that orange line crosses the x-axis, which is obviously going to be, let's choose that color. That's going to be our x2. And if we sort of zoom in into this little square, what you notice is that this point's going to project upwards, that tangent's going to project upwards, that's going to project upwards, and it's going to get closer and closer to that intersection point, which is our star. Right? So let's figure out how do we get a closed form for those points. So what exactly is x1? So x1 is the intersection of the tangent line of f at x0 fx0 with the x-axis. And once we find that intersection point, then we're going to now call x0, x1, and then find x2 with that. So let's see if we can find a formula for this Newton's procedure. So our tangent line is going to have the structure, let's call it y is equal to mx plus b. So we already know what the slope of the tangent line is at that particular point. That's just going to be equal to f prime of x0. And since we want the equation of the line at that point, x0 f of x0, that gives us an x and a y value to figure out what our b should be. So that means we have f of x0 is equal to f prime of x0 times x0 plus some number b for which we need to define, and we can easily solve that equation b to be equal to f of x0 minus f prime of x0 times x0. Right? So once we have our b, then we have that our tangent line has the equation yt is equal to m x plus b. So that is our tangent line. So we want to know when this tangent line is equal to 0, and then we solve for this x for which we're going to call x1. So what we're going to do is notice that we have an f prime x0 in this term and an f prime x0 in this term. So we're going to mandate that f prime x0 not be equal to 0, i.e. it can't have sort of a turning point, a maximum point, a minimum point. It can't have any of those. So if that is the case, then we're going to have x1 plus fx0 all over f prime of x0 minus x0 is going to be equal to 0. And then we have what? So then we're going to have that x1 must be equal to x0 minus fx0 all over f prime of x0. And that's a closed form representation for x1. And then once we have x1, then we're going to find x2 how? So x2 is going to be equal to x1 minus fx1 all over f prime of x1, and so on. So the formula for the Newton's method is xm plus 1 is equal to xn minus fxm all over f prime of xm. And this is true for n is equal to 1, 2, all the way down to whatever value we want to stop. And x0 is our initial guess, with the restriction is that the derivative at each of these iterations, f prime of xk, cannot be equal to 0, else we're going to be dividing by 0, and that iteration method, of course, diverges. Now that we know a closed formula for the Newton's iteration method, now let's apply that to our original example that we used the bisection method before, for which the bisection method didn't really converge that fast. And let's see if Newton method does any better. So if f of x is equal to x minus 2, then we know that the derivative of f of x is going to just be equal to 2x. So that means the Newton iteration method, xk plus 1, is going to be equal to xk minus f of xk, which is going to be xk squared minus 2, all over 2xk. So what we're going to do is we're going to choose our x0 to be equal to 1. Obviously, some points are better than others, and you can't choose 0 because f prime of 0 is equal to 0. And that, of course, causes some issues, right? But you could try 1, you could try 2, and compare which one converges quicker. So if we choose 1 to be our initial guess, then x2 is going to be equal to, or x1 rather, so x1 is going to be equal to x0 minus x0 squared minus 2 all over 2 times x0, which is going to come out to 1 minus 2, or 1 squared minus 2, all over 2 times 1, which is 1 minus 2 all over 2, which is 1 plus 1 over 2, which is 1.5, which is the same point, or same midpoint rather, for the bisection method. So that's pretty nice. So the square root of 2 is approximately equal to 1.5. So that's what our Newton's iteration method is saying here. So x2 is going to be equal to 1.5 minus 1.5 squared minus 2 all over 2 times 1.5. And that's going to come out to approximately 1.416 repeated. So that means the square root of 2 is approximately equal to 1.42, right? Which is actually pretty good. And obviously, if we want to do x3, that's going to be equal to 1.416 minus 1.416 squared minus 2 all over 2 times 1.416. And once we plug that in, we're going to get 1.414256, and so on. And if you compare that to, for example, the square root of 2 true value, that's going to be approximately equal to 1.414235. So look at that. We have 41421, 41421, not the 3 though. Let's get that 3 out of there. 41421, 41421. So we have 5 decimal accuracies with 3 iterations of the Newton's method, right? So that's the third iteration, or the third iterate of our algorithm. And for the bisection method, we were only able to get the initial integer value for that, right? Choosing a initial interval of 1 to 2. And we weren't even able to capture the very first decimal. Notice Newton's method gets 5 decimal accuracy with just 3 iterations, with an initial guess of 1, which I think is very, very good compared to the other method. The last thing I want to show you in this video is to show you how to solve equations with these iterative methods. And I'm going to be using the Newton's iteration method, obviously, because it appears to be a lot better than the bisection method in the general case. Right? Now, if you are familiar with some non-classical elementary functions, for example, the Lambert-W relation, then you should already know that the true solution to this is often represented as W0 of 2. But if you do not know what the Lambert-W relation is, then this representation doesn't have any meaning to you, right? So if we were to look at the graph of this particular function, in particular g of x is equal to xe to the x, then obviously we're going to have a graph that's going to sort of look like this, where it crosses the origin. And if we draw the line y is equal to 2, then obviously these two curves cross somewhere there, right? So there's our true solution, whose name is W02, right? But what exactly, in decimal form, is this approximately equal to each other? Notice, whatever it is, if we solve this equation for 0, we're going to have xe to the x minus 2 is equal to 0. So therefore, W02 is the x-intercept of the function fx is equal to xe to the x minus 2. Because when we plug in that particular point, we will get 0 by construction. So if that is our function, so if f of x is equal to xe to the x minus 2, what is its derivative? So its derivative via the product rule is going to be equal to the first times the derivative of the second, plus the second times the derivative of the first, which we can obviously write as just e to the x times x plus 1 if we prefer the factored form. So that means the Newton iteration sequence is going to be xk plus 1 is equal to xk minus fxk, so xk e xk minus 2 all over exk times xk plus 1. So obviously we don't exactly know what is a good point, but obviously you can't plug in points such that the derivative is equal to 0, right? So what makes that equal to 0? So obviously x cannot be equal to -1 and x cannot be equal to minus infinity. Most people won't choose infinite numbers, so that one doesn't make sense, but you cannot choose an initial guess of -1. That's the only restriction that you have here, right? So that's pretty good. So let us choose an x value of 0. So if we choose that, then you can find that our first iteration is going to be exactly equal to 2, because this is just going to be equal to 1, that's just going to be equal to 0, that's 1, that's 1, and then we're just going to be left with -2, which is +2. And then if you plug that element in, you're not going to get a pretty number, but you'll still get a number nonetheless. X2 is going to be approximately equal to 1.42. If we continue this iteration, x3, that's going to be approximately equal to 1.03. So our terms are decreasing, but decreasing to what is the question? So x4 is going to be approximately equal to 0.8755. x5 is going to be approximately equal to 0.853003. And then we have that x6 is going to be approximately equal to 0.85266056. And x7 is going to be approximately equal to 0.852605502014. And one can find that this portion is accurate. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 11 decimal point accuracy. And you should be able to see when it's converging, when you start to get repeated decimal digits over and over again, and it seems to be collapsing on itself, right? So we have 2266005. So we get 4 decimals in one iteration from 5 to 6, which is actually very, very good. So it's actually, oscillating very, very quickly, sort of like in that picture that I showed before, that once you sort of get under that curve where you sort of start bouncing, it actually converges very, very rapidly. And it gets 11 points after 7 iterations, which is actually very, very nice. And in case you're curious of the true value of this number, one can find that W02 is approximately equal to 0.8526055020137725, and obviously we were able to get up through that point with just 7 iterations. So obviously from that we can see that Newton's iteration is very, very useful for solving any equation. So I hope you enjoyed this video, and I'll see you in the next one. Take care.